The last part of section 12.1 deals with limits and continuity. The definition of a limit, the limit of a vector valued function, is given as if r is a vector valued function such that r of t equals f of ti plus g of tj, then the limit as t approaches a of that vector valued function r of t is equal to the limit of each of those individual functions as t approaches a for the I and the j components. Now, if you have the vector valued function for a space curve, then you find the limit of each of those components. Let's do an example. Okay, you can find the limits of each of these vector valued functions. In this case, they're written using component form, but they can also be written using the IJK standard unit vectors. You can go ahead and try these on your own, pause the video, and then come back to see my solutions. So for this example, I'm going to find the limit of each of the components separately and then combine the results to find the limit of the entire vector valued function. Let's go ahead and find the limit as t approaches 0 of e to the t. In this case, we can simply plug in 0. We get e to the 0 equals 1. Let's find the limit of the second component, the limit as t approaches 0 of sine t over t. If you plug in 0 here, you get sine of 0 over 0. So you get 0 over 0. It's an indeterminate form. 0 over 0. I'm going to write that over here. 0 over 0, indeterminate form. So you can use L'Hopital's rule to determine the limit. So the limit of sine t over t as t approaches 0 is going to equal the limit as t approaches 0 of the derivative of the numerator. The derivative of sine t is cosine t, and the derivative of t is 1. Now you can plug in 0. The cosine of 0 is 1. 1 over 1 gives you 1. And the last part here, we're going to find the limit as t approaches 0 of the last component, e to the negative t. That's e to the negative 0, or e to the 0 is equal to 1. So the limit of this vector valued function as t approaches 0 is the vector valued function with components 1, 1, and 1. Okay, let's do the same thing for this vector valued function. Find the limit as t approaches 1 of the vector valued function with components t and natural log of t over t squared. Let's set this up with two separate limits. Find the limit as t approaches 1 of t by simply plugging it in. We get that this limit is equal to 1. Now we want to find the limit as t approaches 1 of the natural log of t over t squared minus 1. And if you plug this in, plug in 1 for t, you get the natural log of 1 over 1 minus 1. And the natural log of 1 is 0 over 0. This is another indeterminate form. So we can use L'Hopital's rule to determine, to find an equivalent limit. So 0 over 0 indeterminate form means you cannot determine the limit simply by plugging in the values. So by L'Hopital's rule, this limit is going to equal the limit as t approaches 1 of the derivative of natural log of t, and that is 1 over t, and the derivative of t squared minus 1 is 2t. This, when you simplify it algebraically, it's equivalent to 1 over t, so we can move that t to the denominator, 1 over 2t squared. Now when you plug in 1, you get 1/2. So the limit of this vector valued function as t approaches 1 is the vector 1, 1/2.